Welcome, welcome. Let's continue with this. So I really hope you enjoyed the conversations, coffee, cookies, and in general, the whole atmosphere here in Belgrade. So this is our database corner here. We have another talk on specifics and internals of vector databases and their scalability. And I'm intrigued to invite here on stage Vardanian from Unum.cloud. Right. So the stage is yours, and please take it from here.
Sure? Oh, wow. Epic. So thank you all for coming. Today we are going to talk about vector search and databases at scale, the topic that is very dear to me personally. I am the founder of a company called Unum.cloud. Aside from this, I used to do some physics in the past, but most of my life for the last 15 to 20 years, I'm coding in C-like languages. Currently, I also run the C++ user group of Armenia. So if you are ever coming to our wonderful country, just let me know. We'd be happy to host you as speakers or participants. So at the bottom there, you have two GitHub profiles. One is my personal, and the other one is my company's profile. And we'll cover a lot of open source projects that you can find over there. So it might be easier for you just to follow the links immediately. And while you do so, I'll warn you that there will be a lot of new memes in this presentation. Well, maybe not that many, but as any responsible CEO, I had to put some memes into the presentation. So without further ado, let's split our talk into a few parts. I'll start with vector search. Then we talk about scale, kind of jumping towards the end. After that, we're going to the topic of databases. And last but not the least, if we have time, I'm going to share a cool project that I've been doing for the last few weeks. I'm pretty sure you're going to love it. So first of all, what's vector search? It's a very simple problem to state. So we all know basic math. We know coordinates like x, y, z. In machine learning, most representations that neural networks produce are actually high-dimensional vectors. So they can be not 3-dimensional, but 300-dimensional, 1,000-dimensional. And the problem of vector search is a problem of finding k approximate nearest points to the points present in your dataset. So quite simple to understand. Lately, people have been using it for all kinds of stuff. So people use it for transformer memory. Transformers are those weird new AI architectures that everyone is talking about, like the ones inside of GPT. People use vector search engines for recommendation systems, and people use them for semantic search. This last one is the simplest one to understand, so let's dive into that one. So a semantic search engine, even though it may sound complicated, it's something that everyone has definitely used. So Google and Bing are two famous examples. Many of you are familiar with Yandex, the co-organizers of the conference, which are also an example of a semantic search engine. So a semantic search is a search system that doesn't search for matching words or tokens. It matches for similarities in the meaning of content. So let's say you can have a textual query searching through images. And the only way to accomplish it is if you have AI decent enough to compare textual representation and an image representation and to say if they're similar. But you are not running AI on every pair of text and image in your dataset. You produce an intermediate representation, a vector. You put them into a vector search engine. And afterwards, every time you search, you encode the query and search within the dataset. So there are a few models that are used for those embeddings producing the vectors. Most commonly, encoders would be BERT-like architectures and decoder-like architectures like GPT, general purpose transformer. Vector search engines are also numerous. The ones that people often use are called SCAN and FAIS. SCAN is from Google and FAIS is from Facebook or Meta these days. And you can compose any neural network and any vector search engine around any data set to build up your own semantically searchable data lake, which is kind of what we do. But the question is, why now? So I've been working on those problems for the last 7 and 8 years, and no one really cared. Until a few months ago, people started talking about AI. The neural networks are getting better and better. They're getting bigger. With size comes increase in accuracy. And once the accuracy is becoming better, people start using vector search engines to navigate vast data sets of transformer memories or representations for different forms of content. And just for companies that I could remember have raised a total of 200, how many? $28 million over the course of 3 months, last 3 months. So this is not a full list. You can probably find more companies. So if there is like so much money being poured into this industry, let's kind of understand what makes up vector search and how to build one. So the problem of finding nearest neighbors in some low-dimensional or high-dimensional space has multiple solutions. The oldest one of them is space-filling curves. It originates in the time of Peano and Hilbert, trying to prove conjecture. But more recently, people have been using stuff like this in systems like Postgres as extensions to actually search for nearby two-dimensional points or three-dimensional points. So the old school indexes for latitude and longitude could have used space-filling curves. Most commonly, not the ones by Hilbert and Peano, but the ones that are Z-curves and similar ones. A more recent thing is k-dimensional trees. That's something that people have been using a lot, maybe since 80s when they started developing video games, because like a special case of k-dimensional trees to a certain extent is an octatree, which is a way of indexing a three-dimensional space. And once you're trying to do some basic ray tracing or try to index the points forming up the scene, a 3D scene in a game, you would need an index like this. A more modern approach is locality-sensitive hashing, but we are going to talk today about the navigable small world graphs, which is the last but probably the most popular these days. It was originally popularized in 2011, but as it always happens, the original implementation may not be one found in everyone's gadgets. So what happened, in 5 years or so, people designed a hierarchical revision of this original algorithm. It's kind of common, you know, like in computer science, when we face a problem, the first thing we do, we throw a hierarchy into it. So like, you're not working with an array, you're working with a tree. And in here, you're not working with a graph or proximity graph, you're working with a tree that essentially goes through multiple layers of graphs. To imagine it, we essentially put a few points into a data set, we find a few neighbors, we connect them together into a proximity graph, and the idea of the hierarchical algorithm is to actually build up layers upon layers of those graphs. The bottom one is the fine-grained one, the top one is the coarse-grained one. You start from the top. Once you find a really good close cluster, you dive into the bottom layer. And you repeat like this until you find the lowest level. Quite simple to understand. It may not be strictly small world graph, to be honest, but we are here to talk more about engineering, not the math part of it. So let's compare a few vector search engines and understand like how they differ. On this slide, I've actually outdone myself. I have not one, but 2 mistakes on the same line. And if you're listening closely, you may already find them. So there is a vector search engine by Facebook called Faiz. There is a vector search engine by Google, but it's not called SPTAG. That's the one by Microsoft. The Google version is called Scan. And the Google version and the Microsoft versions are not implementations of the algorithm that we've just discussed. So they shouldn't be on the slide at all. But I guess this is the artifact of preparing the presentation last moment. And sorry, but in AI we have to do it because every day the state of the art changes. And if I have prepared this talk a week ago, maybe by now it would have been irrelevant. So there's an original implementation for the algorithm, which is the HNSW lib. And there is one by me as well called usearch. So we're going to compare it by performance first, but then we'll cover a lot of other topics like functionality, bindings, ease of use, and ease of integration. So scale, performance. What's that? So for vector search, or actually like for any search, there are 3 primary metrics that describe the quality of your system. The first one is construction speed, how fast you can index through a data set. The second one is the search speed, and the third one is recall. So recall is the measure of quality. Because this is an approximate search system, you kind of have some ground truth in terms of like what is the closest point to your query in your original data set. And you run the algorithm a few times on some sample points from your ground truth data set, you compare the results with your ground truth, and the share of the results that were successful is essentially your recall. And people draw those charts, like the one on the left, that are completely incomprehensible. So like when I look at this, even after so many years in the industry, I have no clue on how to compare those systems. I'm a simple guy, I prefer tables. So there's another metric called NDCG, which is the normalized cumulative gains. There are two repositories that implement benchmarks for those. And if you just run the Docker container and specify which kind of engines you want to run and compare on whichever data set, you will get charts like this. I'm not going to show you any more charts like this in this talk. Instead, we're going to look into logs. So I took a vector search engine. I took some sample data set. I took the perf utility, common in the Linux community. I run the binary. And what I see is a log like this that shows me that the vector search problem has the same issues, or actually the solution to this problem has the same issues as most graph algorithm implementations, which is kind of natural because we're searching through layers of graphs. Obvious. So the problem is, when you look at this, you see 2.4% branch predictions missed. 2.4% may not sound like too bad, but it's actually not even remotely good. Because the modern CPU is a complicated beast. It has a branch predictor at the very top, at the beginning of its conveyor. So if at some point it sees a branch or an if statement, it guesses if it's true or false. And then it continues executing the next instructions that are coming in line. And if the prediction was wrong, it will have to invalidate some of the work it has already done. So if 2.4% of the time you have to actually go back and redo some computation, that's not good. But probably a much bigger, obviously significant part of the slowdown is coming from the backend cycles being idle. So actually the stalls come from the backend of the CPU, which means that we are wasting time waiting for information to be fetched from RAM into the CPU registers. Okay. Let's imagine we understood the problem, which I'm not sure that until now I understood myself. But if we were to guess, the main causes of the bottlenecks would be coming from three places, especially the memory-oriented ones. A, vectors are too big. So if you take a GPT-4-like neural network, it will produce 1,500 dimensional vectors, or like 1,000 dimensional vectors. If every one of them is a float 32 number, it's a 4-byte value. So you end up wasting like 4 to 6 kilobytes just to store the vector itself for every point. And every time you traverse the graph, you have to recompute the distances between your query and every point that you visit within the graph. So this is a lot of computation and a lot of memory to be fetched. Second part is neighbors list are too fat. And by fat, I mean that whenever you store a proximity graph, you actually have to keep together the identifiers of the neighbors of every node. And if those identifiers are too big, again, like 4-byte values, 8-byte values, depending on how big you take those, you will be using different amount of memory. And again, you'll be wasting different amount of time waiting for data to be fetched into registers. Last but not the least, and probably the most generic one that I try to promote is the problem that people use memory allocators inefficiently. And they do too much object-oriented programming. So we've been trained for many, many years that object-oriented programming is good, maybe functional programming is good, abstractions are good. But in my work, in my day-to-day work, I actually have to remove abstractions most of the time and actually just like get down to the bare metal, implement something in assembly, avoid every kind of abstractions. So if I were to think about the solutions to those problems, it's hard for me to solve problems unless I have emojis in a solution, so bear with me. There are some things that no one does. For example, no one stores vectors in doubles because doubles are 8 bytes. And unless you are keeping like some super high resolution latitude and longitude, no one in the machine learning community uses double precision. A lot of the people still use floating point numbers, which are 4-byte values. But in reality, there is not a single large-scale AI lab that we know of, and we know of a lot of AI labs, and we work closely with almost every one of the big names. Almost no one uses 4-byte values anymore. So it's kind of considered a bad tone for the last 4 years. Even when you do training of neural networks, you almost always enable mixed precision if you're using a recent version of PyTorch. But once you get out the vector representations, you can almost always downcast them. So almost all the labs that we know of actually are using BrainFloat 16 or Float 16. I would generally suggest to use the float 16 instead of BF16 because it's IEEE regulated format. Sometimes it's more complicated to use because some of the, let's say, Intel or x86 CPUs do not support F16 but support BF16 for specific kinds of operations like the dot products. My favorite and most often forgotten kind of downcasting is downcasting from float 32 to int 8. So int 8 can only encode values from minus 127 to plus 127, give or take 1, which doesn't matter in this context. But as we'll see here, downcasting even just like to those 200 unique values with equivalent intervals between them is sufficient enough for you to get good performance most of the time in terms of accuracy. But some people are more crazy than we are. They just go all the way to int 4, which is not the way I recommend, to be honest. So the next thing is like the neighbors list are too fat. What do you do in this case? Well, some people would be using uint64 to store the identifiers of the neighbors. The simple solution is to use uint32, which is kind of obvious. Well, but we always go one step further and do the weird thing. So we have a weird type that takes only 10, 20 lines of code to implement, which is uint40. And once you start doing vector search on sufficient scale, you realize that it's almost impossible for you to fit more than 1 trillion vectors on a single node. So realistically, almost all the labs outside of FANG that use our systems, they almost never reach even 1 billion points. FANG goes beyond 1 billion, and we as well, we build systems with billions, tens of billions, hopefully soon 100 billion vectors. But 1 trillion is unreachable. So uint40 is 256 times larger than uint32. It allows up to 1 trillion values. And it's only another 20% memory consumption compared to the other solution. And then probably the most obvious once you start refactoring code, you see too many mallocs, you see too many structures. So if someone was to ask me like how to start getting into vector search, I would recommend looking into a couple of repositories. The algorithms are fairly simple. So when I was implementing usearch as like actually it's probably 10th vector search engine in my career, but it's the first open source one. So I looked at what kind of solutions other people open source, and I immediately saw that whenever we go through every layer of a graph, we go one layer down, and in every layer during the graph traversal, we build up a new priority queue. And given the way it's coded, this means new memory allocations every single time, and the number of those memory allocations is not obvious to predict. So when I see these kinds of lines in any code base, we know that we can rewrite it and make the performance at least noticeably better. Let's see how much. But before we get there, one of the other things that obviously pokes your eye is the fact that whenever you have concurrent accesses to the same graph structure, you have to keep some logs or mutexes around every one of the nodes. So you disallow concurrent updates that will corrupt the structure itself. And again, once I look into the code bases of existing projects, I immediately see arrays of logs and mutexes. The C++'s standard library mutex is at least 40 bytes, depending on the implementation. And even like the code base itself, once you read through it, it says, let's say, a linked list of logs, but in reality, it's just like a continuous array. So there's a lot to be refactored, and that's how I started usearch. When I did so, I threw away almost all abstractions. Instead of using objects, I just have tapes or just regions of memory that I populate myself to achieve maximum data locality. So it's very old school C++. I would say people consider C++ as C with classes. That's not the way I treat it. For me, C++ is C with templates. And I've built this, usearch. So if you take FAIS and you take usearch, you start comparing and benchmarking them. There are two kinds of operations that you perform. You add a vector or you search for a vector in a system. And you can perform this in single entries, in batches, or in bulk operations. So when it comes to bulk operations, the performance difference between us and FAIS is, let's say, 30–40% on a data set that is only 1 million vectors. But once you perform like small batch operations, apparently the implementation of logs in the underlying FAIS library is so inefficient that it requires you maybe like to create separate thread pools. So there's a lot of like this additional bookkeeping that is happening, which makes the overall system really throttle on small batch operations. So on small batch insertions, this is 356% faster, so like 4.6 times. Then we downcast. So instead of doing float 32, we can go down to float 16. And believe it or not, we went from 99.2% accuracy down just to 99.1. So obviously, it's not that hard to like implement float 16. The problem is that if you want to have a compatible library and you want to ship it to every computer out there, the question is how do you compile it? And once we compile, we do not target for machines that exclusively have F16 support. Sometimes we have to backport this functionality through third-party libraries. And this actually sucks. But we'll get back to this when I start talking about JIT. We already had a few discussions here around JIT, but vector search can also benefit from it. And the last but not the least is int8. So int8 is the best type. It's supported on every kind of hardware, even the oldest one. So before the computers supported int16, before they support int32, they supported int8. Int8 is fast, it's small, so you can build up a system that does 300,000 search queries per second, which is in this case 2.6 times faster than the previous solution, and your accuracy is still better. So actually, like the accuracy for int8, for some weird reason, on this specific benchmark, ended up being 0.1% higher than for float 16, which is weird, but sometimes you get those kinds of artifacts when you do approximate benchmarks on like really large data sets. Okay, I've shown you state-of-the-art performance. The question is, can you do better? Of course we can. So the usearch library comes with a few standard metrics or similarity measures out of the box. Most of those are templates, so they can be tuned for your use case. But aside from this, I have a tiny library which I use for experimentation to like put into weird places. This one is called SimSimd. As similarity measures implemented with single instruction multiple data assembly intrinsics. The reason I coded it is that compilers do not really support scalable vector extensions that are new to modern ARM CPUs. So if you use something like Graviton 3 on AWS, you will most likely not be able to like just benefit from those directly. So if you cannot just request your compiler to generate them, we can code them. It's not that hard. And in reality, sometimes, at least on micro benchmarks, I notice insane performance improvements. So with SVE, I was able to perform dot product similarity search at 40 gigabytes per second on a single core. So this is roughly how many times? Like 8 times better than the code emitted by the compiler without extra manual vectorization. Pretty good if you ask me. So this is the QR code. It's easy to find. But I've had so many things on my list, like functionality, bindings, ease of use, ease of integration. Functionality-wise, you can always extend usearch with your JIT compiler of favorite flavor. So like everyone prefers different compilers. Most of the people use LLVM. So there's a system built on LLVM which is called Numba. And Numba allows you to implement custom kernels in Python. You just add a decorator on top of it, and the kernel that you implement in Python will be JIT compiled, and you can pass it down to usearch, which is implemented in C++. So even if I implement and compile usearch for old, outdated hardware, the hot path, which is the similarity measure computation itself, can be ingested ad hoc from a user side whenever you use your library on the target hardware. For people who are a little bit more low level, there is CPPYY, which is a cool project. It is built around Clang, and Clang is a fork of Clang, which is a front end of LLVM again. It comes out of CERN, a physics project. The idea is that with this, even in your Python code, you can define a string. Inside of this string, you have a kernel implemented in C++ or in C. You use CPPYY to compile your kernel implemented in C++ inside of a Python code, and you pass it down to the Python library again. And last but not the least, a couple of weeks ago, I was meeting my friend, who is one of the other low-level developers. There are not too many of us around the globe, and he's responsible for a shit ton, sorry for my French, a lot of different libraries implementing low-level optimizations. Let's put it this way. Almost every time you use any machine learning library, you use his code. So one of his previous projects is called PeachPy. And I wasn't familiar with this project until he showed it to me again as like his university project or something. And in PeachPy, you can assemble an assembly kernel on the Python side and inject it, again, ad hoc into usearch. So this project supports more forms of JIT compilation or like ad hoc assembly injections than probably every other library I've ever seen. A really cool experiment, and this emoji you will not find anywhere, this meme you will not find anywhere else, so try to remember it. So I've talked about features, but then the question is the ecosystem. So when you take FAIS is implemented in C++, it's a relatively bulk project, it has bindings for Python. Okay, great, what's next? In our case, the whole implementation for usearch is just a couple of thousand lines of code for the core implementation. It's super easy to compile. It doesn't have any dependencies. It doesn't need BLAS. It just implements everything internally. So the cool part is that it's a really fun project for you to, let's call it, to practice some programming linguistics or whatever it means. So for many, many years, I haven't had the pleasure of programming in many other languages. And now I've configured all the CI around this project to actually emit bindings in different languages. So the first release cycle of usearch, which took about 2 days to implement a couple of months ago, had C++11 core implementation, bindings for Python 3, JavaScript, and Java. Then a couple of months ago, I had another free weekend, and we coded Rust, Objective-C, Swift, and Wolfram. And now what we've added, or like what we're adding, is C99 binding, Golang, and WebAssembly. And WebAssembly is probably the trickiest because the default runtime uses 32-bit environments. And this system was kind of designed for 64-bit architectures, but will not be too hard to implement. Hopefully this will be ready next week. But more is not always better. Sometimes more is worse. So a lot of the big frameworks, they bring gimmicky stuff that I don't really appreciate. People, especially novice to vector search, often adopt it. And the most commonly used thing out of those is probably IVFPQ, which is a special kind of quantization. So the core algorithm has just 3 hyperparameters. And this solution, using quantization, is just adding a system on top that will make your vectors smaller before you pass them into the vector search system, which is kind of the way to go if you need to solve the problem here and now. But on a real scale, problems arise because you are actually adding an extra part of your pipeline, and it's impossible to track problems such as distribution drifts in the point clouds that you get into your vector search engine. So yes, you get some performance improvement, but you get a lot of problems. And as we've seen, you can already get to the same level of performance without any learned quantization. So the result is a tiny implementation. This slide is actually a bit outdated. The core implementation is 2,000 lines of code, not 1,000 by now. No dependencies, a lot of functionality, just pip install usearch. But I promised to talk about databases. So databases has been like a big, broad term these days. People have been putting JSON into SQL databases. Now they put it into vector databases, which makes me cry. So a database in reality is like more than an index. It's more than just a static file. It's generally like metadata. It's always the rising question if it's like an embedded database or is it like a standalone server. Are you going to do backups? Are you going to do replication? Do you want to do sharding? And at some point, we get to the same problem from different sides. So we have a lot of vector search companies that try to become databases. And we have a lot of database companies that want to become vector search companies. So the first group is companies like Pinecone, Zealous, and CUDA, which will now be adding all kinds of JSON functionality, logs, mutexes, protocols, APIs, whatever you name it. You probably know more terms than I do. And then the second group, databases that we already know, like Redis, MongoDB, and ClickHouse, and many others, would be integrating vector search as an additional form of indexing into their existing functionality. My idea is that those things don't work on real scale. And by real scale, I mean like handling tens of billions of entries on every node, a petabyte plus of data managed on a single node, like 400, 500, 800 gigabits worth of networking on a single node. So this is truly func scale. For you to be able to design infrastructure that scales this far, that is this future-proof, we decided that we want to build everything in a modular way so that once something is outdated, we can replace it with a better solution. So it's not a monolith. It's not like a MongoDB where you just have like a vector search functionality added last week and you cannot pull it out, you cannot replace it, you cannot modernize it by itself. In our case, it's 4 separate libraries. All of them are open source under Apache 2 license. One of them is uStore. It's like a database for you to throw all the stuff that you have into a single place. The second one is uForm. It's a family of our pre-trained transformer models, like the GPTs and the BERTs of the world. But in our case, they're fine-tuned, actually not really fine-tuned, we pre-train, but we tune the design and the architecture itself towards search applications. So instead of producing a vector representation that is a 1,000-dimensional thing, our representations are only 256-dimensional, and we'll get back to it in a second. There is uSearch and there is uCall. So uStore I've actually already covered on the previous Highload, which was a lovely event about half a year ago. So you can go and learn more about it, like from the recordings or on GitHub. uForm we have never covered on those conferences, so they kind of replace OpenAI Clip. Clip is a transformer architecture with 2 towers. One is BERT-like, another one is VIT, Vision Transformer. And the idea is that you train a neural network to align 2 vector spaces. One is a vector space of images, another one is a vector space of texts. Clip is great. It's good for general purpose stuff. But if you want to do search at extreme scale, Clip is too heavy. Our network is maybe like 4 times smaller, 4 times cheaper to run, 4 times faster. Its embeddings are 3 times smaller, and they're much easier to compress further. So we can actually like really reduce the size of our embeddings by a factor of 12 compared to what most other companies are using. Then the last but not the least, like once you start packaging this into services, you want to add an API. And the first thing that Python developers and like machine learning practitioners often do, they use Fast API. Because Fast API has fast in the name, so people assume this will be a good future-proof solution. It's wrong. So one evening, okay, I'll tell the story. One evening this January, I think, I'm sitting in a room in Yerevan, and I'm building up an inference server around our neural networks. And our neural networks, again, can do, let's say, 7,000 inferences per second on a single consumer GPU. This is not enterprise. Then you take Fast API and you realize that the system has a latency, in this case, which is like 1,200 microseconds. But when you run it on a MacBook, not on a server, it can go up to 6,000 microseconds, so essentially like 6 milliseconds. The problem is that once you start like doing the math in your head, you realize that 6 milliseconds is almost enough for the signal to cross the whole country, Armenia, reach nearby country, and come back. So if this is as much time as it's taking to cross the border and come back, versus just talking from one port of the machine to the other port, then there is a problem and it has to be optimized. And for me, it's like a red flag. So I've spent the weekend trying to optimize Fast API and replace like this interface with something else. Any guesses on how fast this can work? So we have 3,000 requests per second on a single CPU core on AWS C7G instances, which is Graviton 3, 64-core bare metal machines. I got down to 20 to 40 microseconds, 230,000 requests per second on a single CPU core, 50 times lower latency, 70 times the bandwidth. And this is just because I used the recent Linux kernel stuff. So Jens Axbo in the Linux kernel 5.19 introduced a feature where they manage and control a pool of file descriptors on their own side. So if you know which APIs to tap into the Linux kernel, you can actually bypass a lot of like slow parts of the Linux kernel and actually implement this the right way. I used a few different dependencies. All of them are seemed accelerated, obviously. But all in all, we have a library that looks and feels almost the same and is like 70 times faster to run, which is kind of enough in this case to do our inference at maximum possible speed. So problem solved. Last but not the least, uSearch, the library that we are covering today for the vector search engine. It has a very simple constructor. It has essentially 3 primary interfaces. One is the constructor, another one is to add points, another one is to search for points. As easy as that. There are a lot of optional constructor arguments that you can use to tune the index for your use case. But all of those, even though they are modular, they have like different problems that are not problems of the implementation. They are fundamental problems of a different domain. So when you try to cram everything into a single solution for a common case, you are ending up accumulating all the problems of every single solution and just multiplying them onto each other. That's why when we try to deploy something in a new domain at a scale, we don't take a general purpose mixture. We take the 4 pieces that we've designed before and we assemble them in a different proportion. Or let's say if we're building up a cluster and we can control what kind of hardware we are buying and what kind of hardware we are renting on AWS, let's say, or some other cloud vendor, what we can do, we can take different number of machines depending on which parts of our pipeline consume the most time. So for a vector search, at the best, on small collections, you can do like 1 million search operations per second, even with our software, with all kinds of assembly optimizations. To make this run fast, you need machines with DDR5, or maybe soon with HBM packaged memory. For a database, you need really fast NVMe SSDs, obviously. In our case, we now also try Optanes. For neural networks, obviously, you need good GPUs. And for networking, well, ideally, you want to have small packets to share, and you want to be running on a recent version of a Linux kernel, which is also surprisingly related to hardware, because sometimes you cannot upgrade to a recent version of Linux kernel as the hardware vendor doesn't support this in their driver. So this is also a hardware problem, even though it may seem as a software problem. So we employ all kinds of dirty tricks to make this run faster, something that you shouldn't do. But UCall originally implemented JSON RPC. JSONs do not handle binary data. So one of the weird things that you can do if you have the crazy twisted mind, similar to mine, what you can do, you can downcast from float32 to int8. You can drop all the negative values, just take integers from 0 to 100, and you can actually fit them into the visible range of ASCII symbols. So instead of converting into base64, some other binary format, and exchanging in JSONs, you can actually essentially make your neural network emit ASCII code that will be used in vector search. So we love dirty tricks like this. You have to escape some characters. For example, like the backslash character, I think it might be the symbol 60, but like you put it out of the range, and it works. OK. Now we got to the final part, which is me telling stories. So I'm sad when I see people just using the technology. I want them to abuse the technology. I want them to misuse the technology. Put the technology in weird places. Apply it to the tasks and the problems that they were never meant to solve. A few weeks ago, actually like USearch I released a few months ago, and then a few weeks ago I published an article called Abusing Vector Search for Text, Maps, and Search. And it kills me that all other vector search companies just do AI. Okay, AI is fun. I've been doing it for a few years as well, but there's so much more that we can do. This is a generic search structure, and it's not really vector search that I'm talking about today. This is similarity search. For any 2 objects for which you can define similarity, even if they have different number of dimensions, or like vectors, one of them is like 6-dimensional, another one is 60-dimensional. You can still define some form of similarity measure, let's say like Jacquard similarity that compares the number of matching scalars in like 2 vector representations, and this would work. So if you want to apply it to text search, one of the things that you can do, you can build up Levenshtein distance that will be operating on strings, which are essentially, again, ASCII vectors. You can tokenize and perform search on arrays of tokens. If you have time series, you can search through time series with dynamic time warping or similar metrics. If you have just latitude and longitudes, if you have like common problems, you can still use Haversine distance to apply USearch to your domain. And one of the cooler stories is about Tanimoto distance. So essentially, recently I was chatting with a friend who's doing some natural sciences, chemistry, and he was telling me, Ash, I'm searching through molecules, but I cannot search through too many molecules. Like my system crashes and like it's way too slow. Can you help me? I pull out the laptop, and I kid you not, it took 10 minutes to implement a custom template overload in C++ that would adopt USearch to a chemistry problem. So now this week, you're actually the first ones to hear that. I'm releasing publicly the largest chemical data set with the largest chemical search ever built, with 7 billion entries in it. It will be like shared publicly by the end of the week. And if any one of you is in natural sciences, I hope you'll check it out. But if I were to sum up like this whole presentation, I would split my recommendations and some of the ideas into two parts. The first one is search specific, as you can see by the first word on every line. So search is a memory bound problem. No matter how much assembly we write or like how cool of assembly instructions we can use like to optimize the compute part, if you have large vectors, like there's probably nothing we can do like beyond a certain point. It's great that our performance is like so high, especially like on smaller collections. But once you have an index that is, let's say, 600 gigabytes or like terabyte or 2 terabytes in size in memory, there will be essentially next to no performance difference between us and FAIS because everything is just like memory bound. You're just waiting for memory to be fetched. So for this to be solved, you have to find the right hardware. For us, it's like DDR5 or HBM. Another thing is that downcasting is oftentimes at least as good as quantization. Don't trust the ads. Do downcasting. Don't do quantization. At least that's my idea, and this is kind of debatable. The two things that are kind of generic, they're not just about search. The first one is about my personal fight against abstractions. So I want the software to be short, concise, and understandable. And if the abstractions do not help me make it a lot shorter, then I would rather not have another level of indirection when I'm reading through code, just to understand what every single line of code is doing. So this is a common anti-pattern, but another one that is probably even more common is that scale breaks things. And I've seen like way too many projects that are built like monoliths, and it took me maybe like 5 first years of building this company to understand how to split our abstractions into separate projects. So today I've shown you 4 of our projects. We actually have closer to 25. None of them, like most of them are not open source yet, but we have a lot of cool low-level technology to be released in the upcoming years. So the ones that we already have are available on GitHub, again, under Apache license. So go check it out and abuse it. Find use cases for it that I've never found. Thank you, guys.
Excellent. Thank you to the master abuser. It always intrigues to hear the stories of people who put poor hardware beyond any reasonable limits. Right, so with this, please rate the sessions. That's important. The feedback is really needed. And now we are moving into the questions and answers. Please, any questions for Ash? Right, gentleman, very persistent gentleman at the very front. Please, go ahead.
Hi again. I'm wondering what's the difference between the benchmarks on DDR5 and DDR4 hardware? Just how much of a drop performance-wise is it for you?
It can be drastic. So essentially, if I take 8-channel DDR4 machine and 8-channel DDR5 machine, even though we often like DDR4 systems that we use are often x86 and like DDR5 systems are often ARM. In our case, we often see like 2x, 3x performance difference. So this is what I would expect, like maybe 2.5x on average.
And does that drop basically brings you to the same performance level as FAIS and Scan? So you both become memory bound, or does it not?
So,
or I mean, what I mean to ask is, would usage perform even noticeably better on the DDR4 hardware, which we need still to run for legacy hardware, which we still have anyway and need to run?
So the faster the medium in which your index fits, the bigger the gap between our solution and second best solution would be, most likely. Or like maybe there's a new solution that I'm not aware of that is even better. So let's say if your index entirely fits into CPU caches, the difference can be drastic. And this is actually like a really interesting topic, bringing us towards not just indexing, but clustering and then indexing. So let's say if you really need to squeeze maximum performance, it makes sense for you to cluster all your data points into different shards and make shards as big as the level 3 cache on your machine. And let's say if you're looking into next generation AMDs and CPUs, you'll be having like a gigabyte of caches. So this is big enough for you to fit a significant number of points into the cache itself. I hope it answers the question.
Yep,
So,
it does. Thank you.
Thank you.
Excellent. Any other questions right here at the front?
Well, thank you very much for a great speech. So I have a question about the hack with int 40. Sounds like we were talking about caching, and won't int 40 cause some unaligned reads? And so cache line misses, probably some values will be splitted between two cache lines. Won't it affect performance?
Yes, it will affect performance, but not noticeably, and sometimes not in the way you expect. So there's like an entire debate about cache associativity and like how you have to organize your memory addresses, at least the ones that you work with a lot, in order like to make the system and like the CPU prefetch them and like fetch them fast enough. So in our case, when I'm building a very, very large index, I'm trying to fit the whole vector and all the neighbors into a single tape that fits, let's say, into 2 or 3 or maybe 4 cache lines at most. And when I have like this simple and regular memory access pattern, where like if I'm reading even like, even if I have like a split line load, I will anyways read the next line as well. So like, yes, this specific load will end up being slower, but it will inevitably bring the next cache line that I'm also going to use. So this is not a performance penalty in this specific design pattern.
Thank you, sounds great.
All right, excellent. Any other questions? Again, well, you are not only persistent, but you are... you put your own words into my mouth, yes.
There was a lady here.
So, front line, please.
On the left.
Which, yes, sorry, I didn't notice that, right? There's a lady over there in third row.
Hi again. It seems to me that to understand how your projects work, we need to understand a little how your words, not mine, crazy twisted mind works. If you it seems like once you face an obstacle or any like decision someone else made, you see it in a different way that rather than normal people do. What is the question you ask yourself, or is there something like this?
So I don't know how to answer, like, but I've been doing this maybe like long enough and too long to see that we need to solve a problem. We want to be able to build advanced smart systems, like intelligence systems of the scale that no one else has ever tried. And we're doing it with a lot less resources than, let's say, FANG companies. So for you to be able to achieve the same level of intelligence or like equally smart and big systems working with large datasets and like so on and so forth, like you need to rethink the whole architecture from the very beginning. Sometimes we would like see a solution that seems like it's good enough, but it obviously has problems here and there. It doesn't allow us to use like custom memory allocators. It doesn't allow us to take control of all the hyperthreading. Like we just start adopting a new library that kind of implements the functionality that we need. And after a while, maybe a few weeks in, we realize that, oh, wow, the problems are bigger than we expected, and it would be easier for us to re-implement everything from scratch after gathering experience for 7.5 years on how to do it properly, than to actually try to patch somebody else's system. So this is a bit of a weird culture. It's well known that this culture doesn't suit well to many big companies, and it causes people to rewrite completely everything, which becomes a hell to manage, a hell to maintain. But if you are like a small deep tech startup who's passionate about achieving state of the art, this is the only way to go.
Thank you.
Excellent. Well, and now that persistent gentleman who now pretends to be disconnected from the audience, right? Your turn for your question.
I'm actually checking out the GitHub repository to find.
Please use the microphone.
Myself, but it isn't there. So, all right, I've just checked the GitHub page, and you were benchmarking F32 implementation of FAIS and so on and so forth.
Yeah.
The question is, I think that there is a mode in FAIS which does the quantization and quantizes the vectors down to 8 bits just as well. And I'm wondering whether or not you benchmarked that as well.
We took a few different modes of working with FAIS. We haven't tried like every single one of them. Most of the quantization systems that they provide are learned quantizers that we generally try to avoid, because when you reach indexes that is, let's say, billions of entries.
In that case, you train on 1 million and then apply that to 1 billion.
Well, the problem there is that once you reach index that is this big, everything again breaks at scale. And once we have one more part of pipeline to debug and understand like where the problem is coming from, we wouldn't want this to be a quantization related bug, that like the system or like trained mechanism for quantization caused our a distribution shift, let's say within the points that we want to add into our index. So in order to avoid such problems, we try to keep the systems as simple as possible. This is actually one of the reasons why all of our implementations are really short. UCall is like a few thousand lines of code, usearch is a few thousand lines of code, uStore is a few thousand lines of code, even though sometimes they're competing with systems that are millions of lines of code, especially like in the databases side.
All right, but in any event, what was the exact mode in phase that you've benchmarked?
That's the index HNSW class, which uses beneath the HNSW index. Sorry for
naturally.
Yeah. Like, but once you go through sources, you see that they have a few classes named similarly. It doesn't use any additional like whatever flat registry of labels to IDs or something like that. So it's as bare bone as it can be to get like the raw performance.
Right. So that was the direct approach, which basically does no clustering.
Yeah. And like
just the graph.
Exactly. And like if you want to add clustering in our system, we think that we want to be modular again. So if you want to do clustering, you can kind of retrofit it. You can have like a 2-step pipeline where you do your clustering or some adaptation first, and then you use usearch.
Right.
Excellent. And then, well, you know where to look for that in the GitHub for the details, and you also can continue this discussion at the hallway. Right. So thank you again. And now the last remaining task for you. You need to choose the best question.
This is tough. So there were a lot of good questions.
But you need to choose one, unfortunately.
Yes. So I think we should value persistence in a sense that building up something like deep techie required us to work for a very long time in a stubborn fashion on a problem that everyone abandoned, and for 7 years until investments, no one cared about it. But for the same reason, I think we should grant the person in the first row for the range of the questions that he had.
That's your choice and your decision. All right, so gentleman at the front row gets the prize, sometime, right? And that's it. All right, thank you once again. So and with this, a round of applause for Ash, please.
Thank you, guys.